and this is essentially the core of our activities. We are doing our best to make a symbiosis between theory, synthesis, and material design, as well as material characterization. Okay, this is embedded in a broader context, which includes application of this, so to say, this prototype, this basic idea of making a symbiosis between theory, characterization, material synthesis, with application in other areas of research, like cell dynamics. It's an ongoing project, universe expansion, exotic phase of water, including the supercooled phase of water, as well as COVID-19 spread work which we published a few years ago. So here are the questions to the professors. Okay, I like to put this kind of, so to say, open questions, which essentially make the basis of our activities. This is to give you an overview of what we are interested in exploring and investigation. So the key question is, how does superconductivity emerge from the anti-ferromagnetic Mott insulating dome? This is essentially a key question. And the second question related to this one is, why do molecular metals superconduct, but for instance, chromium doped vanadium oxide does not? This is one of the core of these presentations. Another question: are critical endpoints relevant for the manifestation of superconductivity? Then we go further. What is the role played by lattice degrees of freedom for the Mott transition and charge ordering? Then we come to an experimental question: how to measure thermal expansivity with subatomic resolution. Essentially, I'm speaking about thermal expansivity measurements with resolution below the Bohr's radius. Another question: how to optimize caloric effects, and why is the Grüneisen parameter so relevant for quantifying this kind of effects? What is the ground state of paramagnetic insulator? It is possible to make use of the EASY model to describe COVID-19 spread. Is there a link between elastocaloric effect and the universe expansion? What about the recognition of the Grüneisen parameter in the Einstein field equations? So this is, as I mentioned before, these are some questions which we plan to address in the following. So here we start. I will present you a very brief overview of our experimental facilities. Essentially, we know it's quite easy to measure the length of a table, of in the microscale. Essentially, it's quite easy to perform experiments or to make measurements of length. However, when you go to the nanoscale region, situation becomes a bit different. This is exactly what we are able to do. We have ultra high resolution dilatometer. It's homemade experimental setup with resolution of variation of length about 0.02 angstrom. As I mentioned, we are below the Bohr's radius. If we measure, essentially I'm speaking about measuring a sample with length of about 1 millimeter or so. Okay, we have it's essentially a capacitive method. We have a fixed electrode, as indicated here in the figure. We have a movable electrode, and the sample is linked. It's actually assembled to this movable electrode. as indicated here in the figure. We use, of course, a 4-point probe method to avoid the kind of spurious contribution to the capacitance. Many, I would say, technical details I'm not going through, but essentially by measuring the variation of the length of the sample, which is connected to this movable electrode, we are able to measure the change in capacitance with resolution of 10 to power minus 6 nanofarad or so. And then we can make a point-by-point derivative, and we obtain the thermal expansion coefficient alpha. Okay, this is possible to be done along the different crystallographic directions of the material we are interested in investigating. And now I show you a picture of how the cells, our dielectrometer cell, looks like. Okay, here is the fixed or electrode, and here is the movable plate or electrode, and the sample is located exactly in this direction here, in this region. So I have to emphasize already that the thermal expansivity is proportional to the heat capacity at constant pressure by means of the so-called Grüneisen parameter, indicated here by gamma. And then actually you could ask, wow, but these are very old-fashioned kind of experiments. Yes, indeed. It's a very, it's basic physics we are talking about. Essentially, what I want to emphasize here with this slide is the following. When we measure the variation of the volume of or the length of a sample as a function of temperature, essentially we are measuring the variation of the free energy F in respect to volume and temperature. Okay, because the thermal expansivity is proportional of the second, the second temperature and volume derivative of the free energy as indicated here in this rectangle. And here you have KT refers to the isothermal compressibility. Okay, there's another way of showing this dependence of the thermal expansivity. You can also write it as the second derivative of the free energy in respect to temperature and pressure. And you have a prefactor here, 1 over volume. So why is this important? This is because once you measure the thermal expansivity, indirectly you are assessing. You have an indirect measurement. I have to emphasize an indirect measurement of the free energy of the system. And this is our lab. We are able to perform various standard measurements like resistance, dielectric constant, polarization, thermal expansivity, magnetic extrusion, current versus voltage measurements in the temperature range 1.4 to room temperature with magnetic fields below 12 Tesla. Of course, we have to go to the lab. I mean, to perform such experiments, you have to make electrical contacts, many technical aspects I'm going through. And now I come to the motivation of measuring the systems I'm going to present to you. This is because in the 60s was suggested by Little, a fellow from Stanford University, that these organic superconductors could be candidates for the, here is highlighted in red. The conclusion of Little is the following. It's concluded that superconductivity should occur even at temperatures well above room temperature. This is amazing, because I don't need to tell you, if you have a room temperature superconductor, technological applications are really broad and of broad interest. The idea is that we have, the idea proposed by Little is that you have a spine, which is indicated here by this in panel A of this figure. And you have side chains, which are coupled to the spine. And then we have kind of a very intricate coupling between the spine and the side chains, which give rise to electronic excitations which are related to the Cooper pairs. I'm not going into details, just to give you a flavor of the motivation in exploring these materials. Phase transitions are well known from our daily life. Now I come to phase transitions. Know the melting of ice, the boiling of water, also in the Alps, you know these pictures. That then to quantify this phenomena, we need thermodynamics. And then I refer here to the canonical book by Eugene Stanley. Essentially, you have here pressure, temperature, phase diagram. You have here the various lines, solid, gas, and liquid, which are separated by distinct phase transition lines. In the end of this first order phase transition line, we have what we call finite temperature critical endpoint. This figure is very important because the materials I'm going to show in the following presents phase diagram which resembles this canonical phase diagram of water, for instance. I have to mention here, in this case, we have triple point, we have the sublimation curve, fusion curve, and the vapor pressure curve. And you can go from one phase to other just by varying either the pressure, by applying pressure in the system, or or varying temperature. We have also, this is also valid for spins. If you have a magnet, you can increase temperature, and we are going to have a critical point. Here, there are some limitations because of Mermin-Wagner theorem, which prevents long-range magnetic ordering at finite temperature for systems with dimension less than 2. And just to give you, if you are not in the, you have not been working in the field, we have different types of phase transitions, like the metal insulator, metal to superconductor, paraelectric to ferroelectric, and so on. So, over 100 years ago, this fellow, Grüneisen, Edward Grüneisen, published a paper in which he showed that, as I mentioned before, by using very basic thermodynamics, he showed that the thermoexpansivity, here is beta, is the volumetric thermoexpansivity, indicated here in the first line of this slide, is proportional to the specific heat. And since we are dealing with solids, we have phononic contributions, electronic contributions, and magnetic contributions, so that we have a corresponding Grüneisen parameter to each of those contributions. Okay, here again the isothermal compressibility, and in the here we have the molar volume. So now I will I put a question: what can we learn? Indeed, I mean, apart from what we I just introduced to you, I spoke before, what can we learn from thermal expansion data? Then I have to refer to a lovely paper published 20 years ago by Zhu, Markus Garst, Achim Roche, and Kim Yalci. These colleagues have shown that at any quantum critical point, the Grüneisen parameter will diverge. And that's the question is, why does this happen? And the answer is, once you bring the system, now it's not a classical phase transition, as I mentioned before, which are driven by thermal fluctuations. Here we have a control parameter, which can be pressure, magnetic field, doping. You bring the system, you cool down the system close to 0 Kelvin, and you tune the control parameter. And by doing so, you go from an ordered phase, for instance, might be or it could be an antiferromagnetic phase, and you apply field, for instance, and you cross a region which has a critical, which corresponds to a critical field. This point is so-called quantum critical point. And then we achieve, for instance, in the case of a magnetism, a ferromagnetic phase. When you are approaching this quantum critical point, you have an huge entropy accumulation because of the competition between different phases. And this is actually in the numerator of the so-called Grüneisen ratio. Essentially, we are speaking here about the singular contribution of the Grüneisen parameter, which is given by alpha over Cp. Cp is the specific heat at constant pressure. And we can write these two quantities as the pressure derivative of entropy in the numerator, and while in the denominator we have the temperature derivative of entropy. Since the temperature is fixed, if you are dealing with pressure-induced quantum critical point, upon achieving the critical pressure, the entropy will increase or will be enhanced dramatically. That's why the Grüneisen parameter is a proper tool to explore critical points. Okay, this transparency is very important. This slide encodes important information. Now let me give you a flavor about correlated phenomena. You have correlated phenomena in nature when you see birds flying in specific formation, as indicated in this figure. You can have also kind of critical phenomena when you have the wind under the action of the wind in the fields. And this is what we call, or it's related to the Ising model, where you have a single site occupation spin either up or down, which are, we have nearest neighbor magnetic interaction. Okay, it's a very simple model. I will introduce a bit more about in the next slides, but then we can have more complex systems. For instance, instead of have a single site occupancy, you can have double occupancy. It's different from the Ising model. This is quite distinct from that. This is described by the Hubbard model. Okay, this is correlated in really correlated phenomena, or strongly correlated phenomena encoded in this picture. So you can have even more complex kind of excitations like spin liquids. And now I come to the paper of Ising, Ernest Ising, published almost 100 years ago, in which he shows for the one-dimensional Ising model under magnetic field, magnetic exchange coupling J Bry, indicated here. You have here an Hamiltonian, which is essentially given by spin operators at site I, with spin operators site I plus 1. In other words, we have only nearest neighbors interaction. And here is the interaction related to, or the energy scale associated with application of field. Okay, either spin up or down. This is the idea behind of very basic, very classical Ising model. So now I give you a flavor about the Mott physics. Essentially, it's a metal insulating transition which is driven purely by electronic excitations. I like to use an example. If you are in a club, you are dancing, you are interacting with your with people around you, and then interaction starts to become relevant. People start to compete the place to dance, and the best way to minimize the energy is to become, so say, localized in a particular position. This is exactly what the Mott transition, I mean, it's an analogy to the Mott transition. Here is shown the extended Hubbard model. It's the formal way of, at least one of the ways to describe correlated phenomena. We have three energy scales. The first one is related to the Hoping turn, which in turn is associated with the kinetic energy of electrons to go from lattice site I to J. You have the creation operators and annihilation operators at site I and J with sigma spins. Okay, this is one important energy scale. The second energy scale is the Hubbard U, the energy you have to pay to put two electrons at the same lattice site, obeying Fermi-Dirac distribution. Here's our number operators I spin up, number operator also index I spin down, and then you have the third energy scale with the so-called intersite Coulomb repulsion, which in turn is associated with the energy you have to pay to put electrons in neighboring lattice sites. Please note that the index are I and J. If you are a student, you are attending this talk, I have to emphasize, once you have a Hamiltonian, you have to diagonalize the Hamiltonian, like in the case of the Ising model. This can be done exactly. You diagonalize, you get the eigenenergies. Once you get the eigenenergies, you put these eigenenergies in the partition function. Once you have the partition function, you can obtain the free energy of the solid or the material or the system you are interested in. And once you have the free energy, you can derive the observables like magnetization, thermoexpansivity, magnetic susceptibility, specific heat, and so on. Okay, this is the very fundamental. Starting from the Hamiltonian, we can achieve a quantity which can be measured in the lab. So now I come to a cartoon from the Mott metal insulating transition. You have a metal, itinerant electrons. When electrons localize, you have here kind of single occupancy. Usually you have long range magnetic ordering, as indicated here, spin up, down, and so on. These are hypothetical two-dimensional lattice. And now I come to the materials. So what is shown here are temperature, pressure versus pressure phase diagrams for various systems. I'm not going to details. You have a very exotic phase, like the Mott insulating phase I mentioned before, spin Pyers phase, antiferro, spin dense wave, and eventually, upon pressurize, for instance, this material, you achieve superconductivity. You have similar phase diagrams for this system, and also for the third system here on the right side, you have even more exotic manifestations of matter, since we do not have long-range magnetic ordering. Instead, we have the so-called spin-liquid phase. So the question is, why? This is one of the questions I put before. Why does these molecular conductors become superconductors upon pressurizing it? But the chromium-doped vanadium oxide does not. This is a fundamental question. If you can answer this question, please tell me after finishing this presentation, okay? Here, the phase diagram of high-TC superconductors. The underdoped dome is a Mott insulator, and then the fundamental question I mentioned before. Now, I just want to skip the materials, and I want to show you what we have done in the last almost 10 years ago, or a bit more. We have explored this region of the phase diagram close to the critical endpoint, as well as the region upon going from metal to insulator. And what we have observed is that upon achieving the phase, the Mott transition line, we observed that the volume of the insulator is bigger than the volume of the metal. This is a subtle effect of in terms of relative volume change of 0.04%. In other words, just to give you a feeling, upon localizing, those electrons no longer take part in the cohesion of the solid, and as a consequence, the lattice reacts, and we have an expansion of the solid. Okay, it's a very anisotropic effect for this class of material, but it seems to be universal. Also, an important result we obtained in the frame of these two works I mentioned before is that we can model the system using a two-dimensional easy model. Essentially, for the liquid gas phase transition of water, we have the difference between the density of the liquid and gaseous phase, as indicated here on the right side. This is proportional to the reduced temperature to power beta, apart from this is the critical exponent actually. And we have done the same because density and volume are somehow proportional, and we have derived exactly in the frame of the easing model, the singular contribution to the specific heat, as well as the singular contribution to the thermal expansivity. And we have observed that while the specific heat follows a logarithmic dependence with the reduced temperature, the thermal expansivity follows a power law. In other words, the thermal expansivity is more singular than the specific heat. In other words, even yet we have here breakdown of the Grüneisen scale. And this is a universal observation. I want to, as I mentioned, I want to give you a feeling what we have been done over the last few years. It means that close to any finite critical endpoint, the Grüneisen scale breakdown. Okay. This was observed, for instance, in the structural phase transition of cerium and in many other systems. We have also shown that the Mott insulating phase is even more exotic. We are dealing with a multiferroic phase, which is corroborated by the systematic dielectric constant measurements. And we have also here lattice effects accompanying the manifestation of the multiferroicity in this system. So I will skip the Griffiths-like phase in the just to mention on the verge of the coexistence region between metallic and insulating phases. Okay, this can be lovely and nicely described by I would say compressible easy model. We have puddles instead of having spin up and spin down. We considered puddles, bubbles of metal, and bubbles or puddles which are composed by insulating phase. And there is a coupling between those bubbles, which we call here delta E, and we have observed, or we have described nicely using easing model plus Avramov's model. I'm not going to details, that upon crossing the metallic insulating coexistence region, we have an electronic drifts phase. Okay. In other words, I mean, one important result here, one important result is that the effective mass is enhanced dramatically upon crossing the first order phase transition line. So the summary of this part is that these systems, we consider these systems as an appropriate playground for exploring various critical or very critical phenomena and correlated phenomena as well. So I will skip the second system. Just to mention, we have explored the Mott insulator dome. Here we have a very exotic ferroelectric phase. Essentially, when you have electrons localized for this class of materials, namely in this region indicated by cyan color, instead of having homogeneous distribution of charges, we have the formation of electrical dipoles, which gives place to the manifestation of what we call ferroelectric Mott-Hubbard phase. We have explored this region. We have also investigated the lattice response associated with the manifestation of this ferroelectric Mott-Hubbard phase. And more recently, we have probed by systematic dielectric constant measurements the character of the ionic contribution to the ferroelectric Mott-Hubbard phase. I come now to the, I will skip this. We have also explored radiation effects, many interesting aspects related to these systems. This is the so-called Fabre salts. And also these systems we consider quite interesting systems to explore various critical phenomena. Now, the last part of this talk, I have, I guess, 5 minutes more, Mahmoud. It's okay?
Yes. We have time.
Okay.
Please continue.
Thank you so much. Now I will give you some flavor about critical phenomena and the so-called Grüneisen parameter. So this I mentioned before. This is namely these two phase diagrams. We have temperature, pressure. It's quite well known from classical textbooks. Now I'm going to focus on the finite temperature critical endpoint. You see that phase diagram of water is somehow similar to the phase diagram of the molecular conductors we are interested in. We have shown that close to any critical, we have extended the work of two collaborators. I'm speaking about that Physical Review Letters paper of 2003. We extended this. We have shown that close to any finite temperature critical point, we have huge entropy or intrinsic entropy accumulation. Okay, and this is what we're going to use to make caloric effects now. Okay, I'm giving you some spoiler. We have shown, we have computed the Grüneisen parameter employing very basic thermodynamic relations to the ideal gas, van der Waals gas, as well as the Fermi gas. Okay, and then in this paper here, I'm just showing you a few years ago. Essentially, just to recall you, we quantify, if you are dealing with the barocaloric effect, namely pressure is the tuning parameter. You have to use the what we call only Grüneisen parameter. If you are using magnetic field as tuning parameter, if you have a magnetic critical point, you have to use the so-called magnetic Grüneisen parameter. And the idea now is how to use this for technological applications and so. This is what we have done. We have described the so-called supercooled phase of water. You know, if you put a bottle of water in the refrigerator, you can, if you cool down slowly, you can have water in under or below 0 Celsius degree, but still in the liquid phase. And interesting is when you grab the bottle of water, you have an instantaneous crystallization of water. And we have described this. It turns out that in that region, the Grüneisen, I mean, when water crystallizes, the Grüneisen parameter is dramatically enhanced. We have computed all observables in the frame of this work, which is also signed by Eugene Stanley. Then I come now to another important result, just to answer one of the questions I put in the beginning of this talk. What the ground state of our insulating paramagnet is? I will answer it. The ground state is ferromagnetic, because matter tends to organize when you cool down the system in order to obey thermodynamic law. Now the caloric effects. I have to emphasize here one of our PhD students, Lucas Esquilante. A lot of contributions to this paper is part of his PhD thesis. We have proposed the realization of elastocaloric effect in some particular systems. And we have actually proposed the possibility of magnetizing material without applying magnetic field, okay, only due to the mutual interactions. Now, coming to caloric effects properly, there is a need, we know, international, to find or to apply very eco-friendly ways of making refrigeration, and caloric effects fit in this frame. And you can, as I mentioned before, you can quantify any caloric effect by employing the Grüneisen parameter. G refers to the tuning parameter, as I mentioned also a couple of times along this talk, pressure, magnetic field, and TS refers to the initial temperature, okay? What we have done is the following. Although the maximization of the so-called electrocaloric effect near a critical point was reported many years ago by Rotzik and fellows in 2011, we have demonstrated in this paper, in this material research bulletin paper, that the close to any critical endpoint, not at the critical point, but close, we have the maximization of the caloric effect due to the entropy accumulation in that region. Then we have proposed kind of ingredients to make maximization of caloric effects. In other words, you have to have coexistence region, you can have dipolar contributions or dipole contributions to the entropy, domain contributions, grain boundary, interface, for instance, coming from conductive paint or other way, structural instability and configurational entropy as it occurs in ice, okay? And you have to bring your system close to the critical point. This is a we like very much this paper because we provided the key ingredients to maximize caloric effects, starting from very basic physics. Eventually, we propose technological applications. This is exactly just to make connection with what we have proposed with literature results. This is a very nice Nature paper by British people. They actually propose, they have measured huge or very large electrocaloric close to room temperature. And we are able to describe this observed effects with our proposal of enhancing the entropy contributions in order to optimize caloric effects. This is the main idea behind. We have also applied during the pandemic the easy model to COVID-19 spread. Instead of having spin up and or down, we have assumed non-infected person, infected person, and the contact, namely our exchange coupling constant is delta E. And we have achieved very nice descriptions. A paper which was accepted by community. I mean, we have used concepts of magnetism for very practical applications. I will skip this. This is almost the, I mean, just finishing. This is just to show you that recently we were able to identify the Grüneisen parameter in the Einstein field equations. It's really funny because people make use of what they call perfect fluid picture to describe the expansion of the universe. And essentially the energy, I mean, pressure is proportional to the energy density by a so-called equation of state parameter. They call this omega. And we have identified this parameter as the Grüneisen parameter, and we can explain analogously to what we have observed to condensed matter physics, namely in the Mott insulating transition, very anisotropic effects. We can explain the so-called anisotropic expansion of the universe in an analogous way to what we have observed for real materials. Okay, this kind of also very interesting and funny applications from concepts of matter, condensed matter physics to cosmology. Perspectives, we have worked also in light-induced phenomena in silicon. I will skip this. Just to mention, because part of this audience is has been working in nanophysics or related phenomena in nano scale. I want to mention that there are some recent studies considering the manifestation of superconductivity in interfaces, as well as possibility of realizing barocaloric effect on graphene, as I described before, which can be quantified by the Grüneisen parameter. Just for the sake of completeness, for those who are not familiar with caloric effects, you have to apply, let's take, for instance, a magnetocaloric effect. You have to bring the system to a particular temperature, the initial temperature, without field. Then we apply magnetic field, you reduce the entropy, and by doing so, you fix the system has to be isolated from the surrounding. You have to bring the system to keep the system in a condition to avoid heat exchange with the surrounding. Then you have to remove the tuning parameter adiabatically. When you do so, you have a natural cooling of the system because it's an adiabatic condition. The entropy has to be constant, and you have to compensate magnetic energy with the thermal energy. That's why you have caloric effects. We have open positions for master, PhD, postdoc, as well as visiting professors. In particular, we could consider the possibility of applying for BRICS projects or collaboration projects. And with this, I want to thank you for your attention, and I finish my presentation.
Thank you, Mariano, for your time and providing us with a nice and comprehensive presentation. It's time for question. If anyone has question, please raise his or her hand up. Then, okay, Prof Maza, please ask your question.
Thank you so much, Prof de Souza, for this outstanding and a comprehensive talk indeed. It was inspiring.
Thank you so much. It's lovely from you.
Thank you. I have a really number of questions, but I would limit myself to just some. What is sure is that definitely there are so much interest from our side towards your activities and towards your group. In terms of light-induced phenomena, we know that, how can I say, you are right that some phase transition can be photo-induced.
Yes.
Well, and I must admit, one of the systems which was really puzzling for our side, and we will definitely exchange some literature in that regard, is chromium oxide escolite.
Okay.
Chromium oxide in its escolite structure has a phase transition. It's a Néel, I think, type transition, magnetic one, around 37 degrees Celsius.
Okay.
And it happened that this phase transition can be photo-induced by infrared radiations. And this phase transition, or this light photo-induced in effect transition, is a purely electronic. It's the valence of the chromium which is triggered. I would be delighted to see, to explore how we can embark in such a kind of investigations, both in a form of thin films and nanoscaled powders. And also you have highlighted interface superconductivity. Reich very early he has showed that the team from Technion, Haifa, there is indeed a superconductivity induced by protonation in tungsten oxide. And really, since Reich passed away, may his soul stays in peace, that subject just died. And we are really extremely interested to follow up on it. In particular, that we are capable to make nanoplates, very high quality nanoplates, tungsten oxides. And also Makarova and colleagues from Germany have published extensively on proton-induced magnetism in carbon-based materials. And I would like really to initiate something in this regard. I will exchange with you by email at the beginning.
Oh, yes. Actually, these are really. First of all, I have a lot of questions as well. you saw
Sure.
in the beginning of my talk.
Yes.
I would say the topics you mentioned are really quite exciting. The light-induced phase transition are really a topic which we have room to work together. It's just a matter of defining the materials, the crystallinity, should we make kind of electric field polarization, what is the energy range we should work, what is the temperature range as well, should we perform this under magnetic field or not, what do we want to discover, how can we contribute to the field. This is a potential, I would say it's indeed a common topic of interest.
Yeah, we will definitely work on it. Definitely.
Regarding the tungsten oxide, this is, you know, tungsten is one of the elements with highest
Melting point.
melting point, and you'll have also, because of this high melting point, you have Debye temperatures pretty high. People, I have to emphasize one thing here. People at Weizmann Institute, Technion, have been working really so wonderful in many fundamental physics. I'm glad to hear from you this about people from Technion. This is also something that we have common interest, and we should also define how to synthesize the material properly, more or less the same questions or the same parameters I mentioned before, and then target some points to really to focus on and go further. How could we go further? I think the first, the initial, first step would be you give a webinar in our group or in our university, like this we have. You are proposing here. I'm glad to be invited. Then we can, meanwhile, we can fix kind of cooperation or visits, or we can write a joint project. I would say we have potential to make high standard and cutting edge physics together. This is more or less something I can, this is my feeling here from what we presented as possible projects and with the boundary conditions we have for.
Definitely, there are a number of opportunities within the framework of IBSA, India, Brazil, South Africa, or the BRICS. There are quite a number of opportunities via the ICTP also, and the TWAS, and via the UNESCO Chair. I will present the UNESCO Chair, and you will see that there are opportunities of mobility, exchange of senior and junior fellows. Allow me, please, just to come in for the techniques. You have mentioned that your technique of expansion, the expansion resolution is of around 0.02 angstroms.
Yes.
Is it correct?
Is it correct? It's below Bohr's radius. You know, Bohr's radius is about half angstrom.
Yes.
But this is for a sample or a specimen of length of about 1 millimeter or so.
Yeah, and that brings me to the size of the samples. These experiments are run mainly on, I do suspect, correct me if I'm wrong, on crystals, isn't it?
No, it's on crystals, yes. It's on crystals. I mean, you can have polycrystalline samples or single crystallines. If you have kind of colloid, or if you have, then you have to find a way, like a sponge, to, so to say, to host the material in order to cool down the system.
Okay. No, we will be definitely working on it. Thank you so much, Prof. De Souza.
Pleasure.
It was just inspiring, and I will follow up with you straightforward. Just
Thank
give
you so
us
much.
a week. Give us a week, but in the meantime, I will liaise with you, sending you some literature.
Great.
Thank
Great.
you.
Well, I thank you so much. It was really a great pleasure to be here with you.
Thank you.
Okay.
Thank you, Prof. Maza. Any other question? Meanwhile, Prof, in one of your slides, you were talking about hoping parameters between surfaces and interfaces. You were writing the Hamiltonians.
Yeah, I can show
Yeah,
you.
yes. I was wondering that for writing these Hamiltonians, what kind of formalism are you using?
Oh, it's not mine, unfortunately, Mahmoud.
Okay,
This is actually this is literature results. Okay, this was proposed by Hubbard.
Yeah, yeah, because I was thinking, is it one of my interesting topics that we can also contribute for modeling and simulation.
I see.
For example, using non-equilibrium Green's function formalism or tight banding, this kind of things also we can contribute at this point.
Let me, you speaking about this.
Yes.
I know.
These surfaces and this, yeah.
Yeah, this is actually not this TIJ, this hopping term, is related. Yeah, this is actually related to electrons. I mean, but not for the interface, as far as I understood your point. Not necessarily. It's for the correlated electrons. I mean, for each electron.
Yeah, for example, two surfaces that we have next to each other, then for transport, that's the formalism that we're usually using for considering the transport, quantum transport, actually.
Perfect. Yeah. This is would be kind enough to repeat your question?
Yeah, no, I was just wondering that I see your formula that you wrote here, that is mentioning that you used somehow Green's function formalism. This is the relation that you have written here. Is an interpretation of that Green's function formalism.
Yeah,
physically. And then hoping parameter, yeah.
Yeah, it is. Yes. What I have to emphasize here, Mahmoud, is that people, we have published on this. If you measure the lattice constant, if you solve the structure, and this we have done for one particular system. Really very nice synchrotron radiation experiments. Then people from density functional theory made use of those structural parameters in order to obtain the temperature dependence of the Hubbard parameters. Yeah. This is the way, what I can tell you, like experimentalists, that people work, maybe, I mean, you and your colleagues have worked on this, but this is very nice because, it's nice partially, because ab initio was initially proposed to really to give us information about the stability of solids and so, Yeah. But people made use now, I mean, just a couple of years ago, we have measured the structure, as I mentioned before, and then people made use of the structural parameters as starting point, as input parameters to derive the Hubbard parameters, namely bandwidth over U, Hubbard U, as a function of temperature, including the hopping term you mentioned before.
Yeah, that's very interesting that you can include temperature to these calculations. It's very nice. Yeah.
Yeah, this was really a very important paper because you are able to follow the enhancement of the degree of correlation in the system upon cooling, upon varying temperature.
Yeah. Okay. Thank you very much.
Great.
Any other question? Okay, I don't see anyone question. Let me check in the chat box. Yeah, our colleague Kobe has a question. Can you see the chat box?
Let me
Mariano?
just, yes, I see. Then experimentally, since most Mott transition occur at finite temperatures in real materials.
In real systems.
In real systems. Yes, the Mott transition occurs for the systems we have explored, these molecular conductors. It occurs around 13K or so, 1.3. But for the chromium doped vanadium oxide, it occurs above room temperature. It's indeed finite temperature phase transition. It's not, as I mentioned, I mean, maybe it exists, but to my knowledge, it's still not reported Mott insulator quantum phase transition. Okay. Yes.
Okay. Thank you. Thank you, Mariano, again for very comprehensive, for very comprehensive presentation. So we will be in touch for more collaboration and and the projects that Prof Maza mentioned. So okay. Thank you very much.
Thank you so much. Thank you. And you, thank you, Professor Matza, Mahmoud. All the best. Thank you.
Thank you very much. Have a nice day. Bye.